Hello everybody and welcome back to the Forum for Learning and to part 4 of lecture 2 in the Biology 101 lecture series. So in this video we're going to attempt to answer these 4 questions here. So we're going to talk about what covalent bonds are, what polar and non-polar covalent bonds are, and we'll talk about kind of the different types of covalent bonds with respect to single, double, and triple bonds. And we'll finish off by talking about how covalent bonds are oriented and how that affects how molecules are shaped. So without further ado, let's get started. Okay, so covalent bonds. So covalent bonds are bonds that form when atoms share one or more pairs of electrons. And again, this sharing happens in order to obtain a stable octet or a stable valence shell electron configuration. So covalent bonds form when two atoms share one or more electrons. Right, and the key word here is share. So covalent bonds, we talked about ionic interactions in part 3 of lecture 2, but covalent bonds occur when, they form when the difference in electronegativity between two atoms, so the delta electronegativity between two atoms is between 0.0 and 1.7. So when we talked about ionic interactions, we discussed that ionic interactions form when the electronegativity difference between two atoms is greater than 1.7. So when it's less than 1.7, you end up having covalent bonds. So when the difference in electronegativity isn't large enough, like it is here, right? It's only between 0 and 1.7. Rather than a complete electron transfer that occurs in ionic interactions, you end up with two atoms sharing electrons. So again, the key word here is with respect to covalent bonds is the sharing of electrons. So let's look at an example here. So let's look at the molecule of hydrogen, right? And it's just hydrogen bonded to hydrogen, right? Now, we talked about the octet rule and that there are exceptions to the octet rule, hydrogen being one of them, right? So hydrogen has one proton, right? And that's why it's the atomic number of hydrogen is 1. And if you have one proton in a neutrally charged molecule, you'll have the equal number of electrons. So in this case, you have one electron as well, right? So, and this one electron, remember we talked about electrons are the ones that sort of affect reactivity and the properties of an element, or the chemical properties of an element. This one electron is located in its only shell, right? Because hydrogen only has one shell, and so this is located in the valence shell, right? Because it only has one shell, so it's also the outermost shell. So it's also located in the valence shell. So because again we mentioned that hydrogen is an exception to the octet rule, it only needs 2 electrons to fill its valence shell, right? Because it only has one valence shell, and we talked about in the previous videos that the first shell can only contain a maximum of 2 electrons. So because hydrogen has one shell, its valence shell can only contain 2 electrons, right? So hydrogen already has 1 electron, right? So in order for it to get into the stable configuration, it needs 1 additional electron, right? So because this valence shell needs 2 electrons total to fill it up and for hydrogen to be stable. And so one's already located in the nucleus, or one's already located in the atom, the periphery of the atom, that's inherent to the hydrogen atom, and then you need 1 additional electron. So so what does that mean? Well, that means that when two hydrogen atoms come in close proximity, what happens is that the respective nuclei, so the nucleus of one hydrogen atom, will begin to attract the electron in the other hydrogen atom. But because both atoms are the same, right, which means that they have the same electronegativity, both nuclei will exert the same kind of pull on those electrons. And so what happens is, because the electronegativities are the same, which means that the attractive forces between the nuclei and the electron and the other atom are the same, what's going to happen is they come together, the two atoms come together and each share an electron with the other atom. So let's write that down. So when two hydrogen atoms come together, right, when they come together, or rather they come in close proximity with each other, their respective nuclei will begin to exert the same pull or attractive force for the electron in the other atom, right? And again, why? Because the delta electronegativity here is 0, because they're two identical hydrogen atoms. They both have the same electronegativity, so the difference between the electronegativities is 0, which means that because they have the same electronegativity, they will both exert the same kind of level of force on the opposing atom's electron, right? So what happens is, at the end, is that a covalent bond will form, right? So, and this formation of the covalent bond is a result of the electron orbitals of the two atoms overlapping, which again results in increased stability for both hydrogen atoms, because now both hydrogen atoms have 2 electrons total in their valence shell, because it's a transient sharing, right? So there's a hydrogen atom here, there's a hydrogen atom here, and so what happens is this hydrogen atom will kind of overlap here, and this hydrogen atom will overlap here, and so they both share these two electrons. And so this hydrogen atom at any given time will have 2 electrons, and then this hydrogen atom also will have 2 electrons, because they're both orbitals are overlapping each other, right? So again, hydrogen being an exception to the rule, but it needs 2 electrons to satisfy that octet and to be stable. And so when 2 hydrogen atoms come together, they share electrons and form a covalent bond to attain that stable state. Okay, so let's look at another example where we have different molecules or different atoms in a covalent bond. So let's go here. Okay, so in this case we have the molecule of, so we have a molecule of methane, right, CH4. And in this case we have 2 different atoms being bonded. So let's look at the structure of the molecule. So you have a central carbon, hydrogen, 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 and hydrogen. Okay, so let's look at carbon first. So carbon has 6 protons, right? Atomic number of 6. And if it's 6 protons and it's a neutral carbon, that means it has to have 6 electrons. So again, 6 protons. So carbon has 6 protons and thus 6 electrons. And these 6 electrons are divvied up between 2 shells. Remember, we said the first shell of any atom has a maximum capacity of 2 electrons. The first shell will have 2 electrons. Will have 2 electrons, and the remaining 4 will be housed in the valence shell. So this set of electrons will be found in the valence shell. Now, carbon is not an exception to the octet rule, so in order to attain full stability, it's going to need to have 8 electrons, or it's going to want to have 8 electrons in its valence shell. So that leaves us with 4 electrons that it needs to share, or that carbon has the ability to kind of share 4 total electrons, right? Share 4 electrons to get to that stable octet rule, or stable octet configuration. So again, carbon has 6 protons, and because that has 6 electrons, has 2 electrons in the first shell that we talked about, and the 4 in the valence shell right here, which means that it needs 4 electrons to satisfy 4 more electrons to satisfy the octet rule and attain stability. This means that ultimately carbon can share with up to 4 atoms and can form up to 4 covalent bonds. So we said 4 can share 4 electrons, which means it can form up to 4 covalent bonds. Right? Okay. So that's a unique aspect of carbon. Now, in this case, the molecule of methane, we also have to talk about hydrogen. We briefly talked about hydrogen a little earlier. So hydrogen has 1 proton and thus 1 electron. And this electron is located in the one and only shell, which is also the valence shell by default. And because, again, it's an exception to the octet rule, it needs 1 additional electron to reach its desired 2 valence electron shell, or 2 valence electron stable state, right? So this needs 1 additional electron. This needs about 4 additional electrons. So what happens is, when 4 hydrogen atoms and 1 carbon atom come into close proximity with each other, what happens is they react and form methane. So we have 4 hydrogen atoms plus a carbon, and that's going to result in the formation of methane, right? So again, because carbon has 4 valence electrons or 4 electrons in its valence shell, so it needs 4 more. Hydrogen has 1, it needs 1 more, and so carbon can form up to 4 bonds with 4 different hydrogen atoms so that both of them can satisfy the octet rule, even though we said that, hydrogen is an exception, but you guys get the point. Okay, so here, in CH4, so in methane, what happens? In methane, the carbon and hydrogen atoms share 1 electron each with each other, right? So carbon will share 1, hydrogen will share the other, and so in each bond, right? Such that after bonding, the carbon atom now has a completely filled valence shell because it's bonding to 4 hydrogen atoms, each of which are going to give or are going to share 1 electron with carbon, right? So in this case, let's draw this again. So in this case, where hydrogen has 1, hydrogen has 1, hydrogen has 1, hydrogen has 1, and this guy has 1, 2, 3, 4, right? This is not a good way of, representing this, but this is just for demonstrational purposes. So here, one of these electrons can be shared with hydrogen, one of these can be shared here, and then you have one of these here, and one of these here, right? So here, carbon and hydrogen will share 1 electron each, right? And so, which basically means that this bond denotes 2 electrons being shared, right? One from each atom. So again, 4 electrons come from the carbon itself in this case, right? Because it's inherent, because carbon has 4 valence electrons already. And then 1 electron comes from sharing with 4 different hydrogen atoms. So now carbon here technically has 8 electrons. Well, not technically, but you get what I'm saying, because it's sharing 4 from hydrogen. It already has 4 in its valence shell, so total 8 electrons. Now hydrogen has 1 electron in its valence shell, and it's going to share 1 of those carbon's electrons, so you have 2 electrons total. And so now you have both of them satisfying the octet rule and conferring sort of stability. And so because of this, after bonding, they both have attained greater stability, right? So the net result for this in this case is covalent bonding, or sharing of electrons, is going to give both atoms greater stability. Okay? So that's really covalent bonding in a nutshell. So now we're going to talk about, what are polar and nonpolar covalent bonds. So let's do that now. Okay, so now let's talk about equal versus unequal sharing of electrons. So we'll talk about equal sharing first. So equal sharing of electrons. So now we said that a covalent bond is merely two atoms coming together to share electrons, right? And so you can have equal sharing and unequal sharing of those electrons in a covalent bond. So let's talk about equal sharing. So when the elements that are in a bond, in a covalent bond, have an electronegativity difference less than 0.5, so between 0 and 0.5, there's going to be equal sharing of electrons because both nuclei in that bond exert similar levels of attractive force on the bonding pairs. So how does this happen again? So we have when the delta electronegativity between the two atoms in a covalent bond is less than 0.5, we end up having equal sharing of electrons across that covalent bond. And why is that? Well, that's because, again, like we said, if the electronegativity is essentially the attractive force that the nucleus of an atom exerts on the electrons of another atom, right? And so if the difference in electronegativity is very small between two atoms, that means the attractive forces that each of them have on the other one's electrons are going to be fairly the same, right? So if the difference is not that high, the attractive forces are going to be the same, and so both nuclei will exert similar levels of attractive force on the bonding electron pair. And again, this is because if the delta again being the difference between the electronegativity of the two atoms involved in a bond are less than 0.5, you'll have equal sharing of electrons because both nuclei will exert similar levels of attractive force on the bonding pair of electrons. Okay, so let's look at a couple examples. Now, we discussed the hydrogen molecule as well as molecule of methane, right? So let's look at hydrogen again. So in this case, we have in this case here, you have two hydrogen atoms bonded together via a covalent bond, right? And across that bond, two electrons are shared, one from each hydrogen, basically. And so in this case, because the two atoms involved, which are these two guys right here, because they're identical, right? Because they're both hydrogen atoms, and so because they're identical, because they're the exact same atoms, they have the same properties, which means that they have the exact same electronegativity, right? So here, the delta electronegativity is 0, right? Because they're the same atoms, which means they have the same electronegativity. Difference between the two is nothing, so 0, okay? So what that means is, if the electronegativity difference is 0, that means that both nuclei, so the nucleus of either hydrogen atom, will exert this same attractive force on the bonding electron pair, right? Which means that there's going to be equal sharing. So for example, let's just redo this here. So the attractive force that the nucleus of this hydrogen exerts on this electron pair is going to be identical to that of the attractive force that the nucleus of this atom exerts on the bonding pair of electrons. And so because you're going to be identical poles, you end up having, it's kind of like if you have, say for example, tug of war, if you have two people that are just as strong as the other, you're going to have, nobody's going to go anywhere, right? So the rope is not going to get tilted to one or the other. The electron pair in this case is not going to be closer to one or the other. They're going to be, the pole is going to be identical, so you're going to have completely equal sharing of those electrons. Okay, so now this is a case where we talked about two identical atoms, right? So if you have two identical atoms, it's likely going to be, or it is going to be equal sharing because they're identical atoms, which means they have identical electronegativities, which means the difference is going to be 0, which means equal pull of those electrons from both atoms, equal sharing, right? So now let's look at a case where you can still have fairly equal sharing but different atoms. So let's talk about methane. We talked about methane here. So a molecule of methane, right? So here, in this situation, so we're looking at specifically the carbon and hydrogen covalent bond, right? There's 4 of them in this methane molecule, but we'll just focus on one because all the bonds are the same. At least the carbon-hydrogen bonds are the same. So in this case, you have the 2 atoms involved in the bonding in this covalent bond here there are carbon and hydrogen. So in this case, they're not identical atoms, right? So you have 2 different elements or 2 different atoms, and so they're going to have different electronegativities. But in this case, the delta electronegativity between the carbon and the hydrogen atom, meaning the difference in electronegativity between carbon and hydrogen atom, is going to be less than 0.5. Okay, it's actually specifically 0.4. And so because it's less than 0.5, that means that both nuclei will exert similar levels of attractive force on the bonding electron pair, right? So they're not, like we said, the carbon and the hydrogen, they're not identical atoms, right? But the difference in electronegativity, they're fairly close in the electronegativities of one another. And so because the electronegativity difference is 0.4, it's less than 0.5, which is the rule we said, right? If electronegativity is less than 0.5, you'll have equal sharing. And so in this case, they're not going to be exactly equal, right? Because there is an inherent difference in electronegativity between the 2 atoms involved, but it's going to be, that difference is going to be marginal. So carbon will exert, so in this case, carbon has the higher electronegativity. So carbon will exert a slightly higher attractive force than the hydrogen atom, but that difference is going to be marginal because, again, the difference is just 0.4, which means they're going to have similar levels of attractive force, meaning mostly equal sharing of the electrons in this bonding pair of electrons. Okay, so that was that. Okay, so let's go back to what we said, right? We said that when we have a difference in electronegativity between the 2 atoms involved in a bond of less than 0.5, you're going to have equal sharing of electrons, right? And so what that means is, again, both nuclei will exert similar levels of attractive force on the bonding pair of electrons, resulting in fairly equal sharing of electrons, right? And so this equal sharing of electrons results in what's called, so we said this is a covalent bond, right? We said that the sharing of electrons results in a covalent bond. Equal sharing of electrons results in what's called a nonpolar covalent bond. Okay, so it's nonpolar. So if there's equal sharing, which results from when there's delta electronegativity of less than 0.5, you'll have what's called a nonpolar covalent bond. Okay, and so now let's talk about what happens when there's unequal sharing of electrons. Alright, so now let's talk about unequal sharing of electrons. So you mentioned that equal sharing of electrons happens when the delta electronegativity between 2 atoms is less than 0.5. Right? So in this case, with respect to unequal sharing, this is when the atoms in a bond have a difference in electronegativity between 0.5 and 1.7. And when that happens, there's going to be unequal sharing of electrons. And this is, again, because the nucleus, in this case, of one atom will have a higher electronegativity and will exert a greater attractive force on the bonding electron pair than the nucleus of the atom with the lower electronegativity. So let's write that down, right? So in this case, unequal sharing of electrons will happen when the difference in electronegativity between the 2 atoms in a bond is between 0.5 and 1.7. Okay, and so when the 2 atoms in a bond have electronegativity difference of between 0.5 and 1.7, you end up with unequal sharing of electrons. And this, again, as we said, is because the fact that the nucleus of one atom, the one with the higher electronegativity, right, will exert a greater pull or attractive force on the bonding pair of electrons than the other atom. And this is the one with the lower electronegativity, right? So again, electronegativity is the tendency of an atom to attract electrons. And so in this case, if there's a significant difference in electronegativity between the two atoms in a bond, in a covalent bond, you're going to have unequal sharing, because the nucleus of the atom with the higher electronegativity will exert a greater attractive force or pull on the bonding electron pair than the nucleus of the atom with the lower electronegativity. Okay, so let's look at an example here. So let's look at a common example, right? So example, let's look at water, right? Good old-fashioned water, H2O. So let's just split that out. So it'd be H, oxygen, hydrogen. Okay, so in this case, we have two covalent bonds, and they're identical covalent bonds. They're oxygen-hydrogen covalent bonds, right? So we have, so let's look at one of those bonds, right, and kind of what's going on in one of those bonds. So in the hydrogen-oxygen bond, you have two atoms, right, involved in the bond, and in this case, they're not identical because you have oxygen and hydrogen, and the difference in electronegativity between oxygen and hydrogen is about 1.4. So oxygen has an electronegativity of around 3.5, and hydrogen has an electronegativity of about 2.1. And so here, the delta electronegativity is around 1.4. And that's between 0.5 and 1.7, right? And so what happens? Well, here the oxygen has the higher electronegativity, right? And hydrogen has a lower electronegativity. So in this case, what happens is the oxygen atom, because it has higher electronegativity, will exert a greater attractive force on the bonding electron pair than the hydrogen atom, which has a lower electronegativity, and this leads to unequal sharing of electrons. So here, oxygen will exert a greater attractive force on the bonding electron pair than hydrogen, right? Than hydrogen. And so what that means is there's going to be unequal sharing of electrons, with oxygen kind of getting a greater portion of the electron density in that bond, right? And so what's the result of that? So the result of this is, so let's just blow this up here. Let me just take this out so it's easier for you guys to see. So the result in this situation is that because oxygen is pulling more of that electron density towards itself, it's going to get a slight negative charge. So you're going to have what's called a partial negative charge. So it's denoted as that, right? And because oxygen is pulling those electrons towards itself, because it's, again, greater electronegativity, what's going to happen? Well, oxygen is going to have more of the negative energy, or not negative energy, I should say, more of the negative electrons towards itself, so it's going to have a more negative charge, right? Whereas hydrogen, it's going to have more of the negative charge of the bond put away from it. So in this case, hydrogen is going to get a slightly positive charge, right? Because oxygen is taking more electrons are negative, and so, or it's pulling those electrons closer, electrons are negative, so it's going to have a slightly negative charge. Hydrogen, on the other hand, is having its electrons sort of pulled away from it, so it's going to have a net positive charge, right? It's going to be less negative, which means it's going to be more positive. And so, again, the result of this unequal sharing is that there's going to be a slight negative charge on the oxygen atom and a slight positive charge on the hydrogen atom in the bond. And again, this is because the oxygen atoms greater attractive force causes the bonding pair of electrons to be located closer to the oxygen nucleus and the hydrogen nucleus because of oxygen's greater electronegativity and a stronger pull, right? And so what happens? Well, in this case, it results in the actual physical electron density among both of these bonds, it's gonna result in the bonding electrons being drawn closer to the oxygen nucleus and the hydrogen nucleus. And so in this situation, when we have an electronegativity difference of two atoms in a covalent bond between 0.5 and 1.7, what that's going to do is, again, like we said, there's going to be unequal sharing of electrons. And when there's unequal sharing of electrons, it's going to result in what's called a polar covalent bond. Okay, a polar covalent bond. And so when there's equal sharing of electrons, we said it's going to be a nonpolar covalent bond. When there's unequal sharing of electrons, it's going to be called a polar covalent bond. And so why is that? Well, we talked about oxygen. Let's go back down. Where is this? All right, we talked about oxygen here. So let me just redraw this again. So we have hydrogen, oxygen, and hydrogen, right? And we said here that oxygen is pulling that electron density towards itself, or towards its nucleus. So it's going to have a net negative charge. Hydrogen is going to get the electron density pulled away from it, so it's going to have a net positive charge. And so what's going to happen is, the reason this is called a polar covalent bond, right, due to unequal sharing, is because of the fact that the polarity of the bond is due to the slight separation of charge across the bond due to the unequal sharing. And that results in the presence of two poles at either ends of the bond. So in this case, there's, in the case of water, right, in the case of water, we have unequal sharing across these bonds here and across this bond here, right? Because oxygen is pulling that electron density towards itself. And so because of that, there's going to be two poles to this bond. So if you just isolate this bond here, right? Just isolate this bond here. We have a negative pole here at the oxygen end and a positive pole here at the hydrogen end, right? Because the majority of that electron density or those electrons are located closer to the oxygen's nucleus, and so it's going to have more of a negative charge, right? Because electrons are inherently negatively charged, and so you're going to have a negative pole on the oxygen end and a positive pole on the hydrogen end. And so this is the negative, so this is called negative, or I should say partial negative charge, and the hydrogen is going to have a partial positive charge. And there are going to be implications in biology. We'll get to those, as we go through these lectures, because the implications of the presence of these polar bonds in the molecule, like water, for example, affects how that molecule will interact with other polar molecules. So specifically with water, it's one molecule of water, because it's a polar molecule and it has polar bonds, it's gonna be able to interact with other polar molecules, including other water molecules. So that's a quick overview of. So in this case, now that we talked about, we'll change this to equal sharing results in nonpolar, and unequal sharing results in polar covalent bonds. Okay, so again, just a quick overview. Equal sharing of electrons comes about when the difference in electronegativity between the two bonding atoms is less than 0.5, and that again results in equal sharing of electrons, because both nuclei will exert similar levels of attractive force in the bonding electron pair. And when there is equal sharing of electrons, you end up with what's called a nonpolar bond, because there aren't poles across the bond, right? Because the electrons are located towards the center of the bond, so each of the two atoms will remain in their natural state of charge. There's not going to be poles across that bond. Whereas in unequal sharing of electrons, it happens when you have the delta electronegativity between the two atoms between 0.5 and 1.7. And again, it results in unequal sharing of electrons. And this is because the nucleus of one atom, which is the atom with the greater electronegativity, will exert a greater pull on the bonding pair of electrons than the other atom with a lower electronegativity. And this results in the presence of slight poles, right? Slightly charged ends of each at the end of the bond at each atom, and results in what's called a polar covalent bond. So now that that's done, let's talk about what's next. So we'll talk about single, double, and triple bonds. All right, so let's talk about the different types of covalent bonds. So we said that in a covalent bond, you have two atoms sharing electrons, right? But in the case of a covalent bond, you can have two atoms that are involved in covalent bonding who can share more than one pair of electrons with each other, resulting in multiple covalent bonds, right? So we can have what's called single bonds, double bonds, and triple bonds. So let's talk about each of those. So a single bond. So a single bond is a traditional or typical covalent bond where a single pair of electrons are being shared between two atoms, okay? So a single bond is your traditional covalent bond, right? And what I mean by that is all of the bonds we've talked about so far, the hydrogen-hydrogen bonds in a hydrogen molecule, the carbon-hydrogen bond in methane, the oxygen-hydrogen bond in water, and most other bonds are going to be single bonds, right, between two atoms. And so, like we said, in a single bond, what you have is you have a single pair of electrons are being shared amongst two atoms, right? And so this means that two electrons total being shared, right? And so a single bond is denoted by a single dash. Okay, so it's like X dash Y, right? So in the examples we've talked about before, they include the hydrogen-hydrogen bond in a hydrogen molecule, the carbon-hydrogen bond in a molecule of methane, and then we also have the oxygen-hydrogen bond in water, right? And so that's a single bond. So we also have what are called double bonds. So what are double bonds? So double bonds are covalent bonds where two pairs of electrons are shared between two atoms. So in this case, we have two pairs of electrons being shared. So I should say being shared. And also here, single pair of electrons being shared. And so this means that there are going to be 4 electrons total being shared, right? Two electrons from each atom in a bond. And this is denoted by the double dash, okay? So double dash, and it's going to look like X double bonded with Y, right? So some examples of a double bond are a carbon-carbon double bond, and you can also have oxygen-oxygen double bonds. Okay, so in a double bond, again, it's 2 pair of electrons being shared, 2 pairs, meaning 4 electrons total. 2 electrons will come from one atom, 2 electrons will come from the other atom. Okay, now we can also have triple bonds. So in triple bonds, again, just like single, double, and so on, their triple bonds are covalent bonds where 3 pairs of electrons are shared between the atoms. So in this case, we have 3 pairs of electrons being shared, right? And so this means how many? We have 6 electrons total being shared. And these triple bonds are denoted by a triple dash, right? By 3 dashes, I should say 3 dashes. Okay, and that they're going to look like this: X 1, 2, 3 is bonded to Y. All right, and an example of that are the nitrogen triple bonds that can form, right? So that's kind of the difference between these two kind of bonds. So you have single bonds where a single pair of electrons are being shared, so 2 electrons total, 1 electron from each atom. In a double bond, we have 2 pairs of electrons being shared, which means 4 electrons total, 2 from each atom. And on a triple bond, we have 3 pairs, so 6 electrons being shared total, and it'll be 3 from each atom. Okay, so now these 3 different bonds will have different properties, but for the purposes of this video and for basic biology 101, all you really need to know is the difference in strengths of these different covalent bonds. So the strength goes from triple bonds will have the greatest bond strength, followed by double bonds, followed by single bonds. Alright, so triple bonds are going to have the greatest bond strength, followed by double bonds, followed by single bonds. So these are all the different types of covalent bonds from single, double, and triple. And they're fairly straightforward, right? It's in the name. Single bond means 1 bonding pair, double bond means 2 bonding pairs, triple bond means 3 bonding pair of electrons. Alright, so let's see, what else do we have to discuss? So now we'll finish out this video by discussing how covalent bonds are oriented or shaped. Alright, so now let's talk about covalent bond orientation and shape. So the first thing is that for any given pair of bonding elements, the length of the covalent bond is always the same. So the length, so actually let's start the whole thing. So for any given pair of bonding electrons, right, the length of the covalent bond is always the same. Alright, so what that means is, so we discussed, for example, where is it? So when we discussed, for example, CH4, so let me redraw this down here actually. So okay, so in a molecule of methane, the carbon-hydrogen bond here, the carbon-hydrogen bond here, the carbon-hydrogen bond here, and the carbon-hydrogen bond here, they all have, so all of these bonds have the same length. Okay, so all of the carbon-hydrogen bonds in methane have the same length. So we established that for any given pair of bonding electrons, the length of the covalent bond is always the same. Now, additionally, the angle of each of the covalent bonds in a molecule with respect to the other bonds is for the most part the same. So here, so I should probably write 4 here. Okay, so for a given atom in a molecule, the angle of each of its covalent bonds is, for the most part, the same. Okay, so what do we mean by that? Well, so let's look at methane again. Let's draw that again. So we have carbon here, hydrogen here. We'll draw it this way. Hydrogen there. Oops. Hydrogen there and hydrogen there. Okay. So what that means is the hydrogen carbon hydrogen bond, so this bond angle, will always be the same with respect to the other atoms in the molecule. So again, so for a given atom in a molecule, the angle of each of its covalent bonds with respect to the other bonds is for the most part the same. So what that means is so in a molecule, this bond angle is not going to change, right? It's for the most part the same, just as much as this, just as much as this hydrogen carbon hydrogen bond right here, right? So these all are going to be they're going to remain the same. They're not going to change. And so, so in this case, so for with respect to methane, so in CH4, the angle of all the hydrogen-carbon-hydrogen bonds are the same. And so what that means is that the carbon atom is located centrally and the hydrogen atoms point outward, and all of these bond angles are equal. And so that results in what's called a tetrahedron. So it results in a 3D shape of what's called a tetrahedron, right? And so this 3D sort of structure, it arises as a result of the way the bonds orient, or the atoms orient themselves around each other, so around the central carbon, and also given the fact that the bond angles are all the same, right? So the fact that the bond angles are all the same, and these the bond lengths are all the same, and the bond angles don't change, that gives rise to the actual 3D structure of methane, where you have the central carbon followed by the different hydrogens that point outward. Okay, so the way covalent bonds in molecules are located in space, which is again based off of bond angle and sort of the length of the covalent bonds involved in that molecule, that gives rise to the molecule's three-dimensional geometry, right? And because the bond length between a given pair of bonding elements is the same and the bond angles are fairly the same, the spatial orientation of a covalent bond is fairly stable, which ultimately means that so is the 3D structure. So again, because they have the same lengths, right? These bonds, and they also have similar bond angles. That means that, and because they don't change, in space, that means that the structure of a covalent bond or of a molecule that has covalent bonds is fairly stable, right? So the net result basically is that the spatial orientation of covalent bonds is fairly stable. And what this means is the spatial orientation, which gives rise to the 3D structure of a molecule, right? Like we said in methane, the bond angles and sort of the properties of that molecule give rise to 3D shape, which is a tetrahedron, and that the shape is a result of how the hydrogen atoms are spatially oriented around that central carbon. And because it's fairly stable, that spatial orientation, that means its 3D structure of a molecule is also fairly stable. Okay? Now, another important sort of thing to note is that so we said the spatial orientation gives rise to 3D structure of a molecule, right? But what's also important to note is that the 3D structure of a molecule, especially in biology, gives rise to its specific biological role or function. Okay, so that's a big and a big important point in all of biology, really, that the shape determines function. And we'll kind of go deeper into that and into the later lectures, and you kind of see how that actually stays true. But something else that I should also mention, so we talked about basically thus far kind of what gives the inherent stability to the orientation of covalent bonds in a molecule and ultimately the 3D structure, right? Because we said that the bond lengths are usually the same, or they remain the same, and the bond angles are also the same, which means that overall there's inherent stability in these covalent bonds and in the way these atoms are oriented in space, and ultimately the 3D structure of the molecule is also inherently stable. Now, stability doesn't mean that it's permanent, right? That the molecule cannot change. So in biology, there are instances where the shape of the molecule can change. And so how does that happen, and why does that happen? And the reason this happens is because free rotation around a single bond, so single covalent bond, is possible. And it's important to note that this free rotation is limited only to single bonds. So double and triple bonds cannot freely rotate. So let's look at an example here, okay? So this is a molecule called dibromoethane, okay? So here we have all single bonds, and this single bond specifically over here between the two carbons confers the ability for the molecule to freely rotate. So this is not a rigid structure, and so what that means is that the molecule can rotate, one side of the molecule can rotate, and you can end up having two bromines on one side, or one bromine there, one bromine there. So what that means is, again, that even though for the most part these covalent bonds have great stability, and which results in the shapes of the molecules having great stability, there's also sort of the ability of the molecule to change ever so slightly, and that's due to the ability for free rotation around a single bond. And so the implications of this are pretty huge when you consider really large molecules, really big ones, long chains of single bonded atoms that can freely rotate. That means that there's so many combinations of rotations around any number of single bonds, right? So imagine if you have like a molecule with 10 of these carbon-carbon single bonds that are all able to then freely rotate. So imagine the combinations that can arise, and you have a molecule that's that large. You have all of these points of free rotation. You can have all kinds of different combinations. And so basically what that means is that molecules can effectively alter their structures, right? Especially these large molecules can alter, so they can alter their structures, right? And that's very important, especially in biology, because it's the biological the human body and the biological environment is not always stable, right? It's ever flowing, and so molecules will have to also be able to move and adapt to those conditions as they change. And so that's a very important point. And so overall, although stable, covalent bonds can also be quite dynamic, right? So it's not rigid, set in stone, but they are fairly stable forms of bonding. All right, and so I think that's it for this video. So we covered what covalent bonds were, we talked about what polar and nonpolar covalent bonds were, we talked about what single, double, and triple bonds were, and we just finished talking about how covalent bonds are oriented and shaped, and how they have the ability to change that orientation, right, due to free rotation around the single bond. So that's it for lecture 2, or part 4 of lecture 2. I hope you guys learned something, and as always, stay true, be kind, and never stop learning. Okay, bye.